All right, assalamu alaikum. Let's begin then. So we're doing the differentiation today. We got done with mensuration in our last class. We did a number of practice questions on that. Now, the next topic that we're starting is differentiation. This is only part of the IGCSE math syllabus. It's not part of O-level syllabus. So let's begin with this. Let's first understand what differentiation means, and what exactly we want to achieve by doing this. We've done coordinate geometry before, right? And in coordinate geometry, we learned how to find gradients of straight lines. For example, if you have a function that looks like this, if you have a straight line that looks like this, that it's going this way, and let's suppose there's a point on this line that has coordinates 4 and 5, and there's another point on this line, let's say this point here, and that has coordinates -1 and 0.5. Okay, -1 and 1, let's say. This is another point that I have on this graph. Now, if I were to find the gradient of this line, what I can say for that is I can use y2 minus y1 over x2 minus x1, right? I can say this is y2, this is x2, this is x1 and y1. We can just use the gradient formula, y2 minus y1, that's 5 minus 1 divided by x2 minus x1, which is 4 minus 1, that's 4 plus 1, so that's 4 over 5. That's the gradient of this line, or 0.8. That's the gradient of this straight line. So if we have to find gradients of straight lines, that process is fairly straightforward. We just use the formula y2 minus y1 over x2 minus x1, change in y over change in x, and that gives us the gradient of that straight line. But what about gradients of curves? If we have a curve, how can we find the how can we find the gradient of a curve? How would that work? Let's understand that. Let's say instead of a straight line, we have a curve, and we want to find the gradient of the curve now. Let's take an example. Let's say I have a function that looks like this. This is y here, this is x. And let's suppose I have this curve y equals x cube. This curve actually has a graph that looks like this. It goes like this on the right side. And on the left side, it goes like this. This is a curve that I have, y equals x cube. Now, if I were to ask you, what's the gradient of this curve? What's the gradient of this curve? Can we say anything about the gradient of this curve? Gradient of this curve. Gradient of this curve does not have a single value. It is changing at every single point. Because remember, what does gradient represent? Gradient represents the direction of the graph at any point. So if you have a straight line, it has the same direction throughout. The straight line has the same direction throughout. It's not changing its direction. So for a straight line, the gradient is constant throughout. At every single point, the gradient is 0.8. But when you have a curve like this, the curve is going to change direction at every single point. So if you take this point here, it has a different direction. If you take this point, the curve has a different direction at this point. If you take this point, the curve has a different direction at this point. So the gradient of a curve changes at every single point. Okay. Now, we cannot find the gradient for the whole curve, as in there's not a single value. There's no single value for the gradient of the whole curve. We can only find gradient of the curve at specific points. For instance, if I were to say, what's the gradient of the curve at this specific point, then that makes sense that what's the direction of the curve at this specific point, right? I can find the gradient at this specific point. Let's say this point has coordinates. Let's say the x coordinate at this point is 2. If the x coordinate is 2, and the curve is y equals x cubed, that means the y coordinate here is going to be 2 cubed, which is 8. This is a point that I have on this curve. It has coordinates 2 and 8. Okay. And what I want to do is I want to find the gradient of the curve at this point. Let me call this point something. Let's say this point is A. What's the gradient of the curve at the point A? And that's what you want to figure out. Okay. Gradient of the curve at the point A. Now, one idea is what you learn in graphs of functions generally, that you draw a tangent, and then using the tangent, you take 2 points on the tangent, find the gradient of the tangent using those 2 points, and the curve would have the same gradient as the gradient of the tangent, right? That's one idea that you can use to find gradient of a curve at a particular point. So what you would do in that case would be, you would draw a tangent that looks something like this. You would draw a tangent like this, and then you would say, let's take 2 points on this tangent. So maybe 1 point here, another point here. Find the gradient of the tangent using those 2 points. And then you would say the gradient of the curve at that point is going to be the same as the gradient of the tangent. That's what you generally do when you have to estimate the gradient using the curve, right? However, uh, that's a process that's not very accurate, because you're drawing a tangent manually. One person drawing a tangent will be different from the other person who draws that same tangent. They will have different gradients, and that is the reason in the marking schemes for such questions you have a range of values given for acceptable gradients, because examiner understands that there is going to be chance of error. So one person might get a different value, another person might get another value. But this is one possible method for finding the gradient of curve at a particular point. But since it's not very accurate, we want to have another method using which we can find the gradient's accurate value, right? The exact value of the gradient at this point without having to draw tangents. That is where differentiation comes in. And differentiation helps us find the gradient of a curve at any particular point. Okay. What's the purpose of differentiation? Let me write that down. Using differentiation, what we can do is we can find the exact gradient, not an estimate, but an exact gradient of a curve at any particular point. At any particular point. Okay. Now, how is this going to be done? How do you find the gradient using differentiation? Let's understand that process. And then we'll come back to this example, how to find the gradient at this point without having to draw a tangent. But let's understand how the differentiation process works first of all. We have a general rule for differentiation that we will be using for all functions that we get in our syllabus. If we have a function that looks like this, y equals x raised to power n. If we have a function that looks like this, y equals x raised to power n. Let me add a constant on the side as well. You might have some number multiplying on the side as well. Let's call that number a. If you have anything like this, ax raised to power n. For instance, one such function could be y equals 3x raised to power 4, right? It follows this form. A is 3 and power n is 4 in this case. How do you find the gradient at any particular point for this function? We use differentiation for this. We differentiate this function, and that gives us something that we call the derivative of the function. And the notation that we use for that is, if y is the function, we say dy over dx, derivative of y with respect to x, that's the derivative of this function. What is that going to be given by? A, the constant, that will remain as it is. The constant that's multiplying or dividing, that will not change. It will stay whatever it was. And then you multiply by the power. Power is n here right now. You multiply this thing by the power, so it becomes a times n. And then you subtract 1 from the power. So it becomes x raised to a power n minus 1. That's what the differentiation of a function like this is going to be. So for instance, if you have 3x raised to the power 4, what is the derivative going to be? dy over dx. 3 remains as it is. And then you say, you multiply by the power. So this power n, it comes down and gets multiplied with a. So it becomes 3 times 4. And then you subtract 1 from the power n minus 1, that means 4 minus 1. And if you simplify this, you get 12x cubed. This is how you find the derivative of any function. You have to do 2 steps. You can remember this process using these 2 steps as well. You have to do 2 things. You multiply by the power. That's the first thing that you do. You multiply by the power. That's the first thing you do. So if the power was 4, you multiply by 4 here, first of all. And number 2, you subtract 1 from the power. You subtract 1 from the power. Whatever is the power, you do that power minus 1. Okay. And that would give you the derivative of this function. All right. Now, there are some notations that you need to be familiar with. If you have a function and it's written as y equal to something, when you do differentiation on that, when you apply differentiation process in that, the result that you get is called the derivative of that function. The result that you get is called the derivative of that function. If the original function is y, the derivative is denoted by dy over dx. That's the notation that we use for the derivative, dy over dx. And if the original function is written as f of x, that will also happen sometimes. Sometimes they use the y notation, sometimes they use the f of x notation. If the original function is written as f of x, the derivative of that is written as f prime of x or f dash of x, right? If you have this small dash on top, that represents the derivative of the function. So if the original function is written as y, we write the derivative as dy over dx. And if the original function is f of x, we write the derivative as f dash of x. Okay? These are notations that you need to know about. Dy over dx is the derivative. F dash of x is also the derivative, depending on which form you have in the original function. So if the function is of this form, ax raised to power n, all you have to do is multiply by the power. You multiply by this power here, and then you just subtract 1 from the power. If the power was n earlier, now it becomes n minus 1. These are 2 things that you have to do to differentiate any function, to find the derivative of any function. Now, why is this useful? Why is this derivative useful? Because now that we have the derivative, we can find the gradient at any one particular point. Now, we'll come to that in a few minutes. Let's apply this process in a few more examples to basically get comfortable finding the derivative of any function. So let's say I have another function that looks like this now. Y equals x raised to the power 7. What's the derivative going to be? dy over dx. Multiply by the power. So you multiply by 7 and subtract 1 from the power. So 7 minus 1, what do you get from that? You get 7x raised to the power 6. That's the derivative. Okay. Let's take another example. Let's say you have y equals minus 2 over 5 into x raised to the power 6. Now, the constant that is multiplying outside, that will remain unchanged. So you see in the rule that we had there, the constant a, that remained unchanged. So we do not apply the rule on the constant that's multiplying or dividing outside. That constant remains as it is. The rule is only going to apply this. These two steps are only going to be applied on x power n. Okay. And on that, the rule is that you multiply by the power and you subtract 1 from the power. So let's apply that here. Minus 2 over 5. Minus 2 over 5, that remains as it is. That does not change. You multiply by the power is 6 right now, and you subtract 1 from the power. 6 minus 1, what does that give you? That gives you 5. Now you simplify this, minus 2 into 6, that's minus 12. Minus 12 over 5 into x raised to power 5, that is dy over dx. That's the derivative of y with respect to x. Okay, let's take another example. Let's say we have y equal to 3 over 7 into x raised to power 5. Again, how is the differentiation process going to work now? 3 over 7 remains as it is, right? The constant that's multiplying or dividing, that's not going to change. You multiply by the power, so you multiply by 5, and you subtract 1 from the power. It becomes 5 minus 1, and that gives you 3 times 5, which is 15. 15 over 7, x raised to the power 4. That's the derivative of this function. Okay? That's the derivative of this function. Now, these are simple examples. Sometimes what happens is you have multiple terms in the function. So you have one function in which you have one term plus another term minus another term, right? So you can have multiple terms as well. Let's take an example like that. So let's say you have y equals 4x raised to the power 3 minus 2x power 4, or let's say 2x power 2 plus 5 times x. So we have multiple terms now. How do you find the derivative of this function now? You just differentiate each term separately. Find the derivative of each term separately. So differentiate this separately, and this separately. And then just have the same signs between them. If you have minus here, you have minus here. You have plus here, you keep plus here. What's the derivative going to be? 4x cubed. What's the derivative of 4x cubed? 4 remains as it is, right? 4 is a constant that's multiplying, so that will remain as it is. You multiply by the power, so you multiply by 3. And you subtract 1 from the power, it becomes x power 3 minus 1, which is 2. That's the derivative of the first term. Then you have minus sign here. Minus 2. 2 is multiplying, that remains as it is. Into x squared. Multiply by the power. So power gets multiplied here. Subtract 1 from the power. 2 minus 1, that becomes x power 1. All right. And then you have plus 5 times x. What's the derivative of 5 times x? What's the power of x in this case? The power of x is 1, right? If there's no power on top, that means it's x power 1. Let's apply that rule in this. What do you get from this? 5 remains as it is into 1 into x power 0. When you subtract 1 from power 1, it becomes x power 0. Now let's simplify this, and that gives you 12x squared minus 4x plus 5. That's the derivative of this function. 12x squared minus 4x plus 5. That's how you can find the derivative of this function. All right. Now, there are two special powers that will come very frequently that you should be able to write down the derivatives for directly. One is when you have something like this, y equals, let's say, minus 5 times x. What's the derivative of this going to be? When you apply that rule, you get minus 5 as it is. That's a constant that's multiplying. That remains as it is. Power of x is 1. You multiply by the power, which is 1. If you subtract 1 from the power, what are you left with? You're just left with minus 5. Okay. So we had minus 5x here. And the derivative of that was just this constant that was multiplying outside. Let's take another example. Let's say we had y equals 7 over 3x. What about the derivative of this? Again, 7 over 3 is a constant that's multiplying, that remains as it is. You multiply by the power is 1. You subtract 1 from the power becomes 0, and that also leaves you with 7 over 3. Now that's interesting. Whenever we have x power 1, the derivative is just going to be the number that's multiplying with it, right? So we can write it directly as well. We don't even have to use this process. We can just write down the answer directly. In this case, when the function is minus 5x, the derivative is just going to be this number here. When it's 7 over 3x, the derivative is just going to be this number here. Whenever you have x power 1, the derivative is just the constant that's multiplying outside. Okay. And then what if you have y equal to some constant? Let's say y equals minus 4. What about the derivative of this function? How do you think about this now? Minus 4. Now, minus 4 is just a constant. Do we have any x here? There's no x involved here. So can we say it's x power 0, right? If there's no x, that means it's x power 0 essentially. So if you want to apply that rule, we need some x here, right? So we can think of it like this. If it's minus 4, it means it's minus 4 x raised to the power 0. So I can write this function as minus 4x power 0. Okay. And then what would be the derivative of this now? Let's apply the rule. Now we can apply the rule, right? Because we have x power something now. Minus 4 is a constant that's multiplying, that remains as it is. You multiply by the power gets reduced by 1, it becomes x power minus 1. Now, no matter what everything else is, since you have 0 here, multiplication with 0 is going to make everything 0, and the result is going to be 0 from this. So minus 4 was a constant. The derivative of a constant, it turns out to be 0. Now, is that a coincidence? Is that only for this specific number? Let's try any other random number. Let's say we have y equals 5 over 2. We have this constant. What's the derivative of this going to be? Again, we can think of it like this. We can say this is 5 over 2 x power 0. You apply that rule on this. What do you get from this? 5 over 2 times 0 into x power minus 1. And the result is again 0. And that tells us whenever we have a constant, the derivative of a constant is always 0. Derivative of a constant is always 0. All right. So what was the rule that we had earlier? Earlier, the rule was if we have y equals ax power n, the derivative is going to be a remains as it is. You multiply by the power and you subtract 1 from the power, right? That was the rule. Now, from this rule, we have two specific cases that emerge that we can just remember because that will speed up things for us sometimes. And that is, if you have y equal to k times x, such that the power of x is a number, is 1. So let me actually use the same constant. It says it's ax, y equals ax. Using this rule, the derivative is always going to be the number that's multiplying. You can write it directly. That's what you would get using this rule. And if you just have y equal to a with no x, that means a is a constant, right? The derivative of this is always going to be 0. The derivative is going to be 0. Derivative of a constant is 0. And if you have x power 1, the derivative of that is just the number that's multiplying outside. Okay. Now that's what you need to remember now, this rule, how to find the derivative of any function. You need to remember this rule. Okay. You multiply by the power and you subtract 1 from the power. That's the rule that you have to apply here. Let's do one more example and then we look at the next concept after that. Let's say we have y equals 5x squared minus x plus 3. We want to find the derivative of this, dy over dx. What is this going to be? Let's find the derivative of the first term. You multiply by the power 5 times 2, subtract 1 from the power, it becomes x power 1 minus x. What's the derivative of minus x when it's x power 1? The derivative is just the constant that's multiplying outside. What's the number outside? There's no number here that's multiplying with x. We can say this is minus 1 times x, right? So the derivative is going to be minus 1 here. And then 3, what's the derivative of 3? 3 is a constant. Derivative of a constant is just 0. We can say that's 0. We can just ignore that as well because adding 0 is not going to make any difference. And the derivative simplifies to 10x minus 1. That's the derivative of this function. That's dy over dx for this particular function. Any problems with this? Any questions? No? Okay. Now, why is this derivative important? Using differentiation, remember what I said, we can find the exact gradient of a curve at any particular point. So dy over dx, that basically represents the gradient of the function. Okay, let me write that here. Dy over dx is basically the gradient function of y. Dy over dx represents the gradient of the function. And that is why, if you notice, when we had y equals minus 5x here and y equals 7 over 3x here, these are straight lines, right? Minus 5x is a straight line. 7 over 3x is a straight line. Remember the standard form for y for straight lines, y equals mx plus c. So if you compare with that form, what's the gradient of this straight line? It's just the coefficient of x minus 5. Minus 5 is the gradient. That is why when you find the derivative of this, the derivative is also minus 5, right? The derivative of this is minus 5 because that's the gradient of the straight line. Similarly, here as well, the gradient is 7 over 3 in the next example. So that is why you have the value of the derivative 7 over 3 as well, because it represents the gradient of the function. Similarly, if you think about this, y equals minus 4, what kind of a function is this? It's a horizontal line, right? Y equals some constant, that's always a horizontal line. What's the gradient of horizontal lines? Horizontal lines have a gradient of 0. So that is why whenever we differentiate a constant, whenever we find the derivative of a constant, it's always 0 because the gradient of horizontal lines is 0. Okay, you can also think of it this way for these two specific kinds of functions where you have a straight line like this or this. For the other functions, you apply that rule that we discussed, multiply by the power and subtract 1 from the power. All right. Now, let's go back to that example that we started from. We had this curve, and what we wanted to do was we wanted to find the gradient of the curve at the point A. How can we find that gradient now? Exact gradient without drawing a tangent. Without drawing a tangent, how can you find the exact gradient? This is how it would work. We would say the function is y equals x cubed. You find the derivative of this, dy over dx. What does the rule say? You multiply by the power and you subtract 1 from the power. So multiply by 3 and then subtract 1 from the power, it becomes 3x squared. This represents the gradient function. If you want to find the gradient at the point A, what's the x coordinate of A? The x coordinate of A is 2. So what you do now is you put x equal to 2 in this derivative. You put x equal to 2 in this derivative. What does that give you? That gives you dy over dx equals 3 into 2 squared, and that simplifies to 12. This is the gradient, this is the exact gradient of the curve at the point A. So if you want to find the gradient of the curve at any particular point, what you would do would be, you would find the derivative of the function, put the value of x in that, whatever is the x coordinate at that point, and that will give you the gradient at that specific point. Okay, this is how we can find it. 12 is the gradient of the curve at this specific point, at this particular point. Make sense? Let's move on now. Let's look at the next thing now, and that is that you would have to find the turning points of a curve using differentiation. You can also use differentiation to find turning points of a function. Now, how does that work? Let's understand that using an example. So remember we have done quadratics before. We know how quadratic functions look like, what their shape is. Let's say I have a function that looks like this: y equals 2x squared minus 8x plus 5. This is a quadratic function that I have. Y equals 2x squared minus 8x plus 5. What I want to do is I want to find the turning point of this function. Now, this is a U-shaped curve, right? The curve looks something like this. This is the shape of the curve, right? It's a U-shaped curve. We know that. It's a quadratic function. That's how quadratic functions look like. This point here is the turning point of this function. Now, there were different names that we discussed for this point. We said we can call this a turning point. We can also call this a vertex. That's another name that this point has. In this particular case, since it's a U-shaped curve, we can also call this point a minimum point, right? But there's another name that we have for this, and that is stationary point. Turning points have another name as well. We call them stationary points. Generally, when we refer to turning points in the context of differentiation, we call them stationary points instead. Okay, so stationary points are those points. Stationary points are basically the turning points of any function. Now, you can also find turning points of any function using differentiation. Now, for a quadratic function, we also discussed some other methods earlier. If you remember, for quadratic functions, we discussed this one method for finding the turning point using minus b over 2a formula, right? Minus b over 2a, that was one formula that we could use to find the turning point. It gave us the x coordinate, and then we could find the y coordinate by putting this value back in the function. X equals minus b over 2a, that was one formula. Another possibility was that we could complete the square for a function. After completing the square, we could find the turning point. But those two methods that we did earlier, they were specific to quadratic functions. What about cubic functions? What about power 4 functions? We could not find the turning points of those functions using those two methods, because those two methods were actually specific to just quadratic functions. Differentiation is a process that you can use to find turning points for any function. Okay, it's a general process. Now let's see how this process would work on a quadratic function first of all. Let's look at this curve. On the left side of this curve, you see what's the gradient of the curve. If you were to draw any tangent on the left side, it will be like this, right? Downward sloping gradient. On the left side of the curve, the gradient is negative, right? Because the graph is going downwards, it has negative gradient. On the right side of the turning point, for this particular curve, the gradient is positive because the graph is going in the upwards direction. So on the left side, it's going down. On the right side, it's going up. On the left side, the gradient is negative. On the right side, the gradient is positive. What comes between negative and positive? So when you go from negative values to positive values, what do you have in the middle? You've got 0. At the turning point, at any stationary point or turning point, at any turning point, gradient of a curve is always equal to 0. At any turning point, gradient of a curve is always equal to 0. You can think of drawing a tangent at this point as well. If you were to draw a tangent at this point, this is what it would look like. It would be a horizontal line, right? Tangent at this point would be a horizontal line like this, and that has a gradient of 0. Okay. Now, how do you find gradients of curves? How do you find gradients of curves? Gradients of curves are found using differentiation. So if the gradient is equal to 0, that basically implies that dy over dx, that is supposed to equal 0, right? If the gradient is 0, that means dy over dx, that is equal to 0. Okay? Dy over dx is supposed to equal to 0, supposed to be equal to 0. Now let's apply this idea to this quadratic function. If we want to find that turning point, what we can do is we can find the derivative of this function dy over dx. And let's see what this turns out to be. You multiply by the power. That gives you 4 times x. 2 remains as it is. You multiply by the power, and then you have x power 1. Subtract 1 from the power. Minus 8x. What's the derivative of minus 8x? It's x power 1, right? So the derivative is just going to be this number outside, which is minus 8. Derivative of 5 is just 0. You can just ignore that or put 0 if you want. And the derivative turns out to be 4x minus 8. That's dy over dx. And now what you do is you say, let's put dy over dx equal to 0. Why are we doing this? For finding the stationary point. Stationary point or turning point. For finding that point, we put the derivative equal to 0 because at any turning point, the derivative is supposed to equal 0. For that reason, we put this derivative equal to 0. Okay, so we say, let's put dy over dx equal to 0. What do we get from that? We get 0 equal to 4x minus 8, and the value of x turns out to be 8 over 4, which is 2. X equals 2. That's the x coordinate of that turning point. Now, if x is equal to 2, what about the corresponding y coordinate? Put this value back in the original function. You'll get the corresponding y coordinate from this as well. And the y coordinate is 2 into 2 squared minus 8 into 2 plus 5. You can see what this is. 8 plus 5, 13. 13 minus 16 is minus 3. The turning point has these coordinates, or it's called the stationary point because that's the terminology that they mostly use in this context. Stationary point of this function is therefore 2 and minus 3. That's the stationary point. That's the turning point of this function. Its x coordinate is 2 and its y coordinate is negative 3. That's the stationary point. So how do you find stationary point of any function? You find the derivative and put that equal to 0. Why do you do that? Because at the stationary points, the derivative is supposed to equal 0. This is how we find stationary point of any function. Put dy over dx equal to 0. All right. Now you could do this for a quadratic function, but for quadratic functions, we also used to have some other methods. Why is this method so helpful? It's because we can use this for other kinds of functions as well. For example, we can find the derivatives of cubic functions using this, find turning points of cubic functions using this method, and for any other function as well, we can find the stationary points or the turning points using this method. Let me give you another example. Let's say I have a cubic function now. Let's say I have a cubic function that looks like this. Y equals x cubed minus 12x squared plus 21x plus, or this we have these three terms. This is a function that we have. X cubed minus 12x squared plus 21x. This is the function that we have. And what we want to do is we want to find the stationary points, of this function and their nature. Now that's a terminology that you need to be familiar with. Nature of stationary points. Nature means whether they are maximum or minimum. Whether they are maximum or minimum. For instance, in the previous example, this point here was a minimum point because it was a U-shaped curve. It was a minimum point. If it was a curve like this, then this stationary point would be a maximum point. But now we have a cubic function, right? This is the cubic function that we have. Now for cubic functions, we can draw the graph as well if we want. But let's say we do not know what the graph looks like. Okay. And just using this function, we want to find the turning points. How can we do that? Let's write that function here first of all. Y equals x cubed minus 12x squared plus 21x. How do we start? First of all, we start by finding dy over dx. Okay, how do we do that? We multiply by the power, it becomes 3. We subtract 1 from the power, it becomes x squared minus derivative of this thing. 12 is a constant that's multiplying, that remains as it is. You multiply by the power, you subtract 1 from the power becomes 1. And then 21x, the derivative of that is just 21. This is the result that we get from this. Okay, this is dy over dx. Now, if we are looking for stationary points, what we do is we equate the derivative to 0. Let's simplify this first. We have 3x squared minus 24x plus 21. Let's just save time and put dy over dx equal to 0 directly. Why are we doing this? We don't always put that equal to 0. We only do this when we're looking for stationary points. Why? Because at the stationary point, the derivative is supposed to equal 0, right? So we put dy over dx equal to 0. Why? For finding the stationary points. Okay, that is why we put dy over dx equal to 0. All right, let's do that. We get 0 equal to 3x squared minus 24x plus 21. Now, this equation can be simplified. If we just divide the whole thing by 3, that becomes x squared minus 8x plus 7 equal to 0. Can we factorize this? Yes, 7 and 1 will work. I can do x squared minus 7x minus x plus 7, that equals 0. And that is going to give me two factors. First of all, we can take x common from the first two terms. That leaves us with x minus 1 inside, then minus 1 into x minus 7. And that gives us two factors, x minus 1 into x minus 7, which means either x equals 1 or x equals 7. These are the x coordinates of the stationary points that we have. These are the x coordinates of the stationary points. Okay. Now, how do you find the corresponding y coordinates? You put these values of x back in that original function, and that will give you the corresponding y coordinates as well. Let's do that. When x is equal to 1, put that back in the function. The function is y equals x cubed, so that becomes 1 cubed minus 12 into 1 squared plus 21 times 1. Okay. That will give us the corresponding y coordinate for this first x value. And then for the second x value, we have 2 cubed minus 12 times 2 squared plus 21 times 2. And now we can simplify this. The first one gives us 1 minus 12 plus 21. That's 22 minus 12, which is 10. And the second one, what does this give us? 8 minus 12 times 4 plus 42, that's 2. The second one is giving me y equal to 2. These are the two y values that I'm getting from for this function. Okay. I'm just checking if that is fine. Okay, I'm sorry, I put the wrong point there. That was, so thank you for pointing that out. This is actually 7, 7, 7. Let's change that. 7 cube minus 12. I put 2 there by mistake. It should have been 7. 12 into 49, which is 7 squared plus 21 into 7. But that actually gives me minus 98. That's the other point that I'm getting. So the stationary points that I have are 1, 10, and 7 minus 98. These are the two stationary points that I'm getting. Okay, these are the two stationary points that we have from this. Make sense? Any questions on this? Any problems? No? Okay. Now, once we have these stationary points, the second thing that they wanted us to find was to figure out whether these points are maximum or minimum points. That's the second thing that we have to do now. We have to figure out if these points are maximum or minimum. So is this point a maximum or minimum? Is this point a maximum or minimum? How do we know that? For this, we need to use something that we call the second derivative. The second derivative. Second derivative means to find the derivative of the derivative. So basically, we want to differentiate the function once more, because that is what gives us whether the point is a maximum or it's a minimum. Okay. One way to do it is using sketch. So you can sketch the function, and then using the sketch, you can figure out if the point is a maximum or a minimum. So this function, basically, if you were to sketch it, it would, it's a cubic function, right? Its shape is going to be something like this. Okay. So you can take some points, sketch that function, and then using the sketch, you would know that this point here is 1 and 10, and this point, the other turning point here, this is 7 and minus 98. This is a maximum, and this is a minimum. Okay, now you might be thinking, how is this a maximum? Because the graph is going up here as well. So the graph is going above that point on the right side. And similarly, how is this point a minimum, even though the graph is going down there as well? Even though the graph is going down on the left side, it's going below that point as well. When we talk about maximum or minimum points, we basically are just considering the points close to that turning point. So we are saying this is a maximum because close to this turning point, right next to it, amongst the points that are next to this, it's a maximum point, right? So the points on the right and left, they are below this point. So we say this is a maximum. In proper uh, mathematical terminology that you will see later on at university, this is actually a local maximum, right? Local maximum means it is a maximum point in its own locality, in its neighborhood, it is a maximum, right? But far away somewhere, there might be some point that is going above as well. However, in its immediate neighborhood, in this region, it is a maximum. And similarly, for the other point, in its immediate neighborhood, in this region, this is a minimum. Sorry, there's a problem with one note. It keeps going up. Okay. So in this in its immediate neighborhood, this point is a minimum. So whenever you have a shape that looks like this, you have a maximum. And whenever you have a shape like this, that's a minimum. All right. Now, you could either sketch the graph and you could find whether a point is a maximum or a minimum. That's one possibility, but that's going to take long. We can do it by calculation as well. We can figure out whether the point is maximum or minimum by calculation as well without having to actually sketch the graph. Now, how would that work? For that, we use something that's called the second derivative of a function. Second derivative. Okay. Now, let's first talk about the notation that we use for this. Remember, we said if y is the function, the derivative is represented by dy over dx. This is actually the first derivative. The first time you differentiate the function, we represent it as dy over dx. If the function was f of x, the derivative is going to be f dash of x. If we want to differentiate it once more, we would get something that we call the second derivative. Okay. And the notation that is used for second derivative is with y, the first derivative is dy over dx. The second derivative is d square y over dx squared. D square y over dx squared. Okay, so basically the idea is d over dx, this is actually the operator. This is the operation that we're applying. This means derivative with respect to x. Derivative, d means derivative with respect to x of y. Okay. Now, here, we're saying d square over dx squared. That basically means second derivatives. D square means second derivative that you want to apply the differentiation process once more of what? Of y. Second derivative of y. That's the notation that we use for the second derivative. D square y over dx square. You need to remember that. If it's f of x notation, the second derivative in this case is given as f double dash of x. F double prime of x, f double dash of x. That's the other possible notation that you can use. F dash of x is the first derivative and f double dash of x is the second derivative. Now, what do we do with the second derivative? We have already found the first derivative above, and the first derivative was dy over dx equal to 3x squared minus 24x plus 21. Let me write that here. 3x squared minus 24x plus 21. Right? That was your first derivative. Now, if you want to figure out if this point, if these turning points are maximum or minimum, what you have to do is you have to differentiate it once more. So you find the second derivative of this. You differentiate it again. Okay. What does that give you? D squared y over dx squared. 3x squared, what's the derivative of that? 3 into 2 times x power 1 minus derivative of 24x, that's just 24. And this simplifies to 6x minus 24. The second derivative is given by this, is 6x minus 24. That's the second derivative. Now, if this second derivative is positive, then you would have a minimum point. And if the second derivative is negative, you would have a maximum point. Now, we don't know if it's negative or positive. It actually would depend on the value of x, right? Because it's in terms of x. So what we do at this point is we put those values of x that we had for those turning points. This was one turning point, 1 and 10. And this was another turning point, 7 and minus 28. What we can do is we can input in this x equal to 1 once, and then we input x equal to 7. That's the other x coordinate. X equals 1 and x equals 7. Now, when we input x equals 1, that gives us 6 into 1 minus 24, and that simplifies to minus 18. This is a negative number. When we input x equal to 7, let's see what that gives us. 6 into 7 minus 24, that's 42 minus 24, and that is 18. This is a positive number. Negative 18 is minus 18 is negative, 18 is positive. When the second derivative is negative, you have a maximum point. When the second derivative is negative, you have a maximum point. When the second derivative is positive, you have a minimum point. That's the general rule that we have. If the second derivative is positive, the point that you have is a minimum point. That would be a minimum point. And if the second derivative is negative, the point that you have is going to be a maximum point. Okay. Positive second derivative means minimum point. Negative second derivative means it's a maximum point. Okay. And that's what you need to know about stationary points. I will summarize this here for you. Let me see if I have this chart here somewhere. Okay, so this is what we have done. You would have a function given. If you have to find the stationary points and their nature. So if you have to find stationary points and also figure out if those stationary points are maximum or minimum, this is the process that you follow for that. You find the first derivative, dy by dx. If you put that equal to 0, that will give you the x coordinates of the turning points. Okay. If you find the first derivative, dy by dx, put that equal to 0, that will give you the x coordinates of the turning point. And then if you want to find the y coordinates, put these x coordinates back in the original function, and that will give you the corresponding y coordinates, right? This is what we do for finding stationary points. Find the derivative, put that equal to 0, you get the x coordinates, put them back in the function, you get the corresponding y coordinates. All right. Then if you have to find the nature, whether those turning points are maximum or minimum, for that, we find the second derivative, d squared y over dx squared, or f double dash of x. You can use any of those notations. Find the second derivative, put the values of x in that. So whatever values of x you got from the turning points, you put those values of x in that. Then if the second derivative is positive, you have a minimum point. If the second derivative is negative, you have a maximum point. Okay. This is how we find stationary points and their nature. Does this make sense? Any problems in this? All right, right? We could do this, we could use the same method to find whether this point for the quadratic function was maximum or minimum as well. Although in this case, for quadratic functions, we could just write that directly as well. We know that if the coefficient of x squared is positive, it's going to be a U-shaped curve. So that means it's a minimum point. But if you had to do that using differentiation, how would that work? You had dy over dx above already, dy over dx. That was 4x minus 8. You could differentiate that again. What would be the derivative? Derivative of 4x is 4. Minus 8, that becomes 0. This is the second derivative. This is already positive. We don't even have to put a value of x here because it's not in terms of x. Since it's positive, that means it's a minimum point. Okay, if the second derivative is positive, it's a minimum point. If the second derivative turns out to be in terms of x, in that case, you would have to input those values of x here. First of all, x equals 1, x equals 7 in this case. And then once you have a number out of that, if that number is negative, you say that's maximum. If that's positive, that's a minimum. Okay, so that's about stationary points. And now let's do one last thing that we have in this topic. And that is you would have to find equations of tangents and normals. You would have to find equations, okay, not normals, sorry, only tangents. In A levels, you would be doing normals as well. But equations of tangents to a curve. Sometimes they will also ask you to find these equations of tangents. Now, what do we mean by that? Let's say we have a function that looks like this. So we have a curve and it looks something like this. Okay. This curve has this equation. It's y equals x cubed plus 2. That's the equation of this curve. All right. And now let's say I have some point on this curve. Let's say it's this point here. Or let's take an integer. Let's take this point. What are the coordinates of this point? The coordinates are 1 and 3. Okay. We have this function and we have this point 1, 3. Let's call this point something. Let's say this is A. What we want to do is we want to find the equation of the tangent to the curve at A. At the point A, we want to find the equation of the tangent to the curve. Now, what is the tangent going to look like at this point? It would be something like this, right? It would look roughly like this. We want to find its equation. We want to find its equation. Now, it's a straight line. It's a straight line. How do you find equations of straight lines? We've done this in coordinate geometry. What information do we need for that? In order to write down the equation of a straight line, we need two things. We need the gradient of that line, and we need a point on that line, right? We need two things for this. One, a point. Second, gradient, to find the equation of this tangent. Now, do we have a point on this line? We have this point 1, 3. That is the point at which we're making that tangent. So that point also lies on the tangent, right? So we have a point that's 1, 3. The coordinates are 1 and 3. So yes, the point is known. What about the gradient? Gradient is something that we are not given here. We don't know what the gradient of this straight line is going to be. Now that is where differentiation comes in. That's where differentiation comes in. Because using differentiation, what we can do is we can find the gradient of the curve at the point A. Sorry about that. Okay, so the equation is y equals x cubed plus 3. That's the equation of the curve. Using differentiation, we can find the gradient of the curve at that point. Let's first find the derivative for that. dy over dx, what would that be? You multiply by the power, it becomes 3. You subtract 1 from the power, you get x squared, right? 3 is a constant, derivative of constant is a 0. So the derivative turns out to be 3x squared. We want to find the gradient of the curve at this point, at point A. So we put that x coordinate here. We say, let's input x equal to 1, right? This is the point at which we want to find the gradient of the curve. We put x equal to 1 in this, and that gives us dy over dx equal to 3 times 1 squared, and that is equal to 3. This is the gradient of the curve at the point A. Okay, if you want to find the gradient of the curve at any particular point, the idea for that is you find the derivative and put that value of x in that. So for instance, if you had to find the gradient at, for instance, 0.5, what would be the gradient at this point? You input x equal to 0.5 in that. So in that case, it would be 3 into 0.5 whole squared. That's 3 into 0.25. That would be 0.75. So the gradient of that at this point would be 0.75. Similarly, you can find the gradient at any one particular point of this curve by just putting the x coordinate of that point, right? So finding the gradient at any point, that just requires you to input that value of x in the derivative. Okay. So in this case, we wanted the gradient of the curve at the point A. We found the derivative, put that value of x in that, which was x equal to 1. We put that value of x in that, x equals 1, and that gave us 3. That's the gradient of the curve at the point A. Now remember, tangent is a line that has the same that has the same direction as the direction of the curve at that point. That's how we draw the tangent, that it should be in the same direction as the curve at that point, right? So if the gradient of the curve is 3, that means the gradient of the tangent at A is also going to be equal to 3. Whatever is the gradient of the curve at that point, the gradient of the tangent is going to be the same as well. Okay, that means the gradient of tangent is also equal to 3. So now we can write down the equation of the tangent. Equation of tangent. We have a point on the tangent. The point is 1 and 3. That's one thing that we needed. We have the gradient. The gradient is 3. We have found that here as well. We have these two things. We can write down the equation y minus y1 equals m into x minus x1. You can either use this form or y equals mx plus c. It doesn't matter. Y minus 3, if we call this x1, y1, this would be m. Just input values in this. Y minus 3 equals m, which is 3, into x minus 1. You simplify this, and that gives you y equal to 3x minus 3 plus 3. And the equation of the tangent turns out to be y equals 3x. That's the equation of the tangent at that particular point. So you should remember gradient of the tangent to a curve at any point is equal to the gradient of the curve at that point. Whatever is the gradient of the tangent at whatever is the gradient of the curve at that point, the gradient of the tangent is going to be the same. Okay, so that's the process for finding equation of a tangent. You need a point and the gradient. Point you would already have. If you just have the x coordinate, sometimes they only give you the x coordinate. You can find the y coordinate yourself. So if the x coordinate was, for instance, x equal to 1, you would input x equal to 1 here, and that will give you y equal to 3. So you would have a point. And then for finding the gradient, you put that value of x in the derivative, and that gives you the gradient of that curve at that point as well. So now you have the tangent's gradient and a point on the tangent. You can write down the equation using either y minus y1 equals m into x minus x1 or y equals mx plus c. So these are all the concepts that you need to know for differentiation. First of all, what's the idea of differentiation? What do we use it for? We use differentiation to find gradients of curve at any particular point. Okay, that's what differentiation is used for, to find gradients at any particular point for a curve. This is the notation that we have, dy over dx or f dash of x. What's the rule for differentiation? You multiply by the power, subtract 1 from the power. If you have a constant multiplying outside, the rule does not apply on that. That remains as it is. The rule is only going to apply on x power something. We did some examples on this. If we have multiple terms, you just differentiate each term separately. If it's x power 1, the derivative is just the constant that's outside. If it's a constant, derivative of a constant is always 0. We summarize that here. And then for finding stationary points, what we do is, for finding stationary points, we put the derivative equal to 0. That gives us the stationary points. For finding whether the stationary points are maximum or minimum, if we find the second derivative. If the second derivative is positive, we have a minimum point. If the second derivative is negative, we have a maximum point. And then finally, we learned how to find equations of tangents. You find the derivative, and using that, you can find the gradient of the curve at that point, and that will be the same as the gradient of the tangent. You would have a point already given. If only the x coordinate is given, you can find the y coordinate by putting that value of x back in the function. And then you can find the equation using any method after that. All right, that's how differentiation works. Now tomorrow morning, we'll have a class around 9:45, 9:50, around 10 a.m. most likely. In that class, we will be doing practice questions on this. I wanted to do them today, but we will do them tomorrow instead. What I've done is I've added these questions to the OneNote notebook. You can have a look at that. To OneNote, I've added some questions. Okay, in the differentiation section, we will be practicing some of these questions in our tomorrow's class, inshallah. Okay, so I would advise you to have a look at them before tomorrow, attempt these questions, and then we will do some of them in tomorrow's class. Okay, that's it for today. I'll see you again in the next class.